Hi, welcome everyone. This is West Coast Meetup, a weekly meeting. Today we are continuing the score-based generative models discussion that we have been doing for the last 2 weeks. We will continue looking at the video by Yang Song, the person who introduced score-based generative modeling, and combined that with the diffusion probabilistic modeling to make it the state-of-the-art generative modeling that we have out there today. So as I was saying before that, which I now lost the chain of thought, but so essentially we'll continue with this discussion today. We looked at the basics of score function and the Fisher information last week, and then we looked at how the score matching function was derived from the neural network or a neural network created to estimate the score function. And what we'll see today is continuation of that, where the score matching for the data that we are given will be used or refined using the denoising mechanism, which was discovered independently of the probabilistic. Well, that's what the claim is, independently of the probabilistic diffusion models. And when people saw that had a good scope of combining with the diffusion models, we'll see how then it is used in the diffusion models as well. So that's what we'll cover today. I did send out the agenda on Slack channel, so I'll just read that out quickly. So we'll do a quick recap of slice-based score matching. We'll cover the noise conditional score matching. Then we look at the sampling based on the score matching networks that we have. So essentially leveraging the Langevin Dynamics sampling using score matching. Then we'll see the refinement of the sampling using multi-level noise conditioning. We'll go on to look at the classifier-based guidance based sampling, which is basically what we have in Dall-E, where the classifier is our image text that we send that use this and take your noise and generate this image. Or other examples are I do in painting or out painting, where I say I mask this thing, take the diffusion model and take this image and guide it towards filling it in or changing the color, or when I say changing the color, coloring a black and white image, and so on and so forth. So those are different examples of classifier guided sampling. And then hopefully we can go towards continuous time correlation for infinite noise schedule. So these noise sampling basically have a schedule of noise injection, which are finite steps. But then there is a comparison to if it was made in finite and infinitesimal small diffusion injected, then that process is equivalent to the stochastic process, and there are SDs with the numerical solvers to sample the variables at any random time, essentially. And we'll see that how then they have used those samplers to sample the images by leveraging the stochastic processes, stochastic differential equation solvers. Then there is if time permits, we'll go into the ODE approximation for sampling, where then they are able to use that to showcase that why this is a very accurate, relatively most accurate probabilistic evaluation, and that they do by looking at the MLE and other metrics. And then, I think that is more than enough that what we can cover in one day. So this is what we'll do. Who is the sharing rights? Because I don't want to share, as I may have to go back and forth, and I may not be able to pause when people may have questions. Thank you, Ted. And thank you for putting that agenda there. So we can start at around maybe 25. We did start looking at the slice-based score matching last week, but I will let you decide, Ted. Anything is fine. If you want to start from here, that's fine too. But more or less, it's at around 27 is what we had done last week, where we were just about to start on the noise condition score matching. So I just wanted to cover the first few minutes before we jump to that, so people can refresh what we did last week.
Okay. Yeah, so I thought I would just quickly mention, so like when you're doing Bayesian inference, normally you have to do this giant integration over all the variables if you want to get the normalizing constant that's in the denominator. And so, imagine we're doing something with images. It's 4,000 dimensional problem, at least, whatever other problems we have, millions of dimensions. You can't actually integrate over those thousands or millions of dimensions. You might be able to do it on a sort of small, well-defined physics problem that's 3-dimensional or something like that. So the score function that we're talking about, you take the probability distribution function, P of X, you take the log of that, and then if you look at the gradients of that log probability distribution with respect to X, our inputs, not with respect to any model parameters, then this is the score function that we're talking about. I realize that if this is your first week, that's not really giving you a whole lot, but at least so that you have some intro into what we're doing. And so,
may I just also add
yeah.
that that gradient with respect to data that was shown for the score function. If people have time, they can go and look at the first video by Jeremy Howard on fast.ai, where they start this new series. They started that earlier this year in January or so on diffusion processes. Diffusion based generative modeling. There he gives an elaborate half an hour explanation on why this makes sense in terms of kind of a little more close to without going into mathematical details of why this makes sense. Just wanted to mention that if people are interested in looking at that separately.
Yeah, and okay, I'm going to give the 10-second. So the gradient is going to, point uphill, downhill to where you have the lowest loss, right? If you take the log of some function, it's still monotonic. The things that are lower are still lower, things that are higher are still higher. It has changed sort of the scale of things, but so you can say that the gradient of the probability density is going to, point you to low and high probability areas. The log of it, it's still going to do the same thing. It's just the slopes will be slightly different. So in this case, it's multi-dimensional. So you'll be getting a field that kind of points you towards the high and the low points in the probability distribution. So he had this slide where he says, okay, we're going to have some flexible models, improved generation, better probability evaluation. And it's going to be a problem trying to, again, with this whole multi-dimensional thing. Okay, so first of all, so this bypasses having to do the normalizing constant, but even for this, doing the estimation is going to be difficult. So here you can see this this score, kind of this field that tells you this is the gradient of the log probability distribution. And where I'm trying to get to is even with this, compute-wise, score matching is going to be pretty heavy. And the reason is because if you need to know sort of the gradient with respect to each of your inputs, let's say it's only a 4,000 dimensional image problem, that's still 44,000 backward passes you would need to do for each iteration. Okay, so normally, right, with any kind of machine learning problem we do one backwards pass for each iteration, and that's often slow for big models. Imagine having to do 4,000 backwards passes for every single one. All right, so the solution that he came up with, I don't know, is this slice score matching, where you basically just pick one vector and you just project everything down to that, and you do it in this, you do the one-dimensional score matching problem, but each iteration you do it in a different vector. So that doesn't make sense. Maybe just think of you do PCA, but you do one-dimensional PCA or something. And there's things that we do where we do problems with just the principal components. So the same sort of thing, except in this case, it's not a principal component, it's just a random vector. And you keep doing this, and then that pretty much gets us to where we stopped, Dave. So he says, now if we do this, here's the problem. he shows that you have this random vector you picked and you just basically seem to like dot it with everything. And now you can kind of do this estimation over multiple iterations, and it works. And what we didn't get to is there's no proof that this thing will converge quickly. Okay, he just proved that like it's more mathematically tractable. But as we'll see, the empirical evidence is that yes, in fact, it does converge quite well. I don't know the details if it's like almost as fast as if you did the full score matching thing.
Yeah, so there are some slides later, like within the next 5 minutes, where you can see that it is almost as good as that, and the time performance is absolutely amazing. So
yeah. All right. So any questions? By the way, anybody who's new, like we pause the discussion. In this case, if it's a video, we pause the video anytime anyone has a question. So you can put it in the chat, or you can just question, and that's how we learn, is we dig into stuff.
Since Jerry doesn't have his camera on, I'm going to say Jerry's line, which is there's no such thing as a dumb question.
Yeah.
All of us who've been here for a long time. Oh, Jerry's go.
No. Go for it, man. I actually have a real question, but go ahead.
Oh, I was going to say just we all learn by asking questions about fundamentals, and that's why I keep coming back, after 6 or 7 years, is the questions that are asked by people that do point back to fundamentals can only reinforce understanding, and I always learn from those questions. So please don't feel embarrassed or ashamed to ask what you might think might be a silly question, because they're always awesome.
Well, I'm going to prove that by asking a stupid question. So since we're going random, each cycle, just pick 1 through, what did you say, Ted, 4,000 or something like that? Picking one of those.
I'm saying maybe it's a 4,000 dimensional problem if you have 64 by 64 pixel images, or maybe that's times 3 because it's 3 channels. I don't know, but 12,000. It's not some number that you would say is unearthly, but you would not want to integrate over 12,000 variables.
Well, unless you own a lot of stock in NVIDIA, and then they could say. But anyway, we won't go there. But anyway, in terms of that, that assumes, I don't want to call it uniformity, but the ability to switch between all these. Doesn't that assume, though, that it's just as good to integrate over on number 3045 as it is on number 20?
So just to be clear, this is not a coordinate algorithm. You're not picking one of the 4,000 or 12,000, however many dimensions. You're picking a random vector that could have components of all of the different dimensions.
Oh, okay. Never mind. Ignore my question. I see where you're going with that then.
Yeah.
Okay.
There are other algorithms that are like coordinate ascent. This is pick a full dimensional random direction. I don't even know if I think it's scaled so it's unit length, but like otherwise it's any full vector.
Okay. Thank you. So we're just taking a deep slice through one of those guys. Okay.
Yep.
Cool. Thanks.
And just that, the devil is in the details. So of course, we are walking through this deck, or this presentation, which covers many, many papers, which have a lot of details in there, which we are definitely skipping past. So that's a good question, Jerry. And as Ted answered, but if you want to know more details, we'll have to dig into the paper later.
Okay.
Yes. And then, as you said, Dave, the Yang Song's blog is probably the best place to go a little deeper and then also get references to the specific papers.
Right.
All right. Any other questions? If not, I will hit play. All right.
Uh-oh. Anybody else not hearing that?
Yeah, I cannot hear anything.
Sorry, I forgot to check the box, didn't I? I'm gonna have to stop sharing and reshare. 1 sec.
No problem.
integration by parts to eliminate the dependency on the ground truth data score. This gives us the sliced score matching objective. And in sliced score matching, there is no trace of a Jacobian anymore. Instead, we have vector Jacobian vector product. And this term is much more scalable to compute. So this is actually not hard to see because we can rewrite the vector Jacobian vector product as an alternative form on the right-hand side. So this just requires to swap the location of v and s theta within the gradient operator. So now I will show you how to compute this vector Jacobian vector product very efficiently. First, we just need one forward propagation to get the output of s theta. And then we can directly compute the inner product between v and s theta. So this amounts to adding one additional neuron to the computational graph. And next, we can compute the gradient by doing one bank propagation. And as the last step, we just need to compute the inner product between v and the gradient. So the whole procedure only requires one bank propagation, which is much more efficient compared to the vanilla form of score matching. So this is how sliced score matching works in practice. We just sample a mini bunch of data points from our dataset. And for each data point, we sample one single projection direction from our distribution of PV. And then we form the empirical estimate of the sliced score matching training objective using the empirical mean over our sampled data points and those projection directions. So the projection distribution PV is typically a simple standard Gaussian distribution, or sometimes better, you can use Rademacher distributions, which are uniformly distributed sign vectors. And then we can use stochastic gradient descent to minimize our empirical objective for sliced score matching. And if you want better performance or equivalently lower variance of our training objective, you could potentially use more projections per data point. So that concludes the discussion of sliced score matching. There exists another approach called denoising score matching that can also bypass the computational challenge of vanilla score matching. The idea of denoising score matching is to add additional noise to the data point to help us compute the trace of the Jacobian term. So to perform denoising score matching, we need to design a perturbation kernel, which we denote as Q sigma. So Q x tilde denotes the perturbed data point, and x denotes the original noise-free data point. Q sigma can typically be a Gaussian distribution with mean x and a standard deviation sigma. So after convolving this perturbation kernel with our original data distribution, we get a noisy data distribution Q sigma of x tilde. The key idea of denoising score matching is to estimate the score function of this noisy data density instead of the score function of the original data density. So of course, when sigma is very small, you can approximately view the score function of the noisy density as equivalent to the score function of the noise-free density. So the magic happens when you estimate this score function of a noisy data distribution. So you can use some arithmetic derivation to write down an equivalent form to the denoising score matching objective, which I gave at the bottom of this slide. So in this new form, what we need to compute is just the gradient of the perturbation kernel. So because we designed the perturbation kernel by hand, usually this perturbation kernel is a fully tractable distribution. So computing this gradient is very efficient and it can be done analytically. But the drawback of denoising score matching is that since it requires adding noise to data points, it cannot estimate scores of the noise-free distributions. And what's worse, when you are trying to lower the magnitude of the noise, the variance of denoising score matching objective actually becomes bigger and bigger and eventually explode. So there is no easy way to use denoising score matching for noise-free score estimation. So we can actually derive the formula of the knowledge score matching very easily, but I guess due to time reason, I will skip this part. And it's not hard to find this derivation from the original paper of the knowledge score matching. So as a conclusion, when you want to apply the knowledge score matching, you follow a similar procedure as sliced score matching. First of all, you sample a mini batch of data points from the data density. And then you sample a mini batch of perturbed data points. So usually for one data point, you sample a single perturbed data point by adding the additional amount of noise to perturb the chosen data point. And then you can form the empirical estimation of the denoising score matching loss by approximating the expectation using empirical means. So in the special case of Gaussian perturbations, you can further simplify the denoising score matching loss function. And then you can just apply stochastic gradient descent to minimize this objective function to train your score model. So in practice, if you want it to work well for estimating score functions of noise-free data densities, you need to choose a very small sigma. But as I said, when sigma is very small, the variance of this objective will explode. So there is a trade-off, and you need to find the sweet spot. So here are some experimental results. We first want to compare the computational efficiency of a sliced score matching and also denoising score matching versus the vanilla version of score matching. We consider the problem of training energy-based models, or equivalently, we are considering the problem of training score functions from noise-free data. So the first figure shows how much time is needed to perform each iteration of various algorithms as a function of data dimensionality. So when data dimensionality increases, all those algorithms will take more time to perform one training iteration. But clearly, score matching in the color of brown scales the worst. And in contrast, sliced score matching and denoising score matching, which can be abbreviated as SSM and DSM in the figure, they scale much more preferably compared to score matching. And in terms of the actual performance of a score estimation,
thank you for pausing. So the left figure was the performance, the time gap, right? Yeah, thank you, Ted. So this is the time gap in the exact score matching, which is the y equals x kind of line. Of course, there's a different dimensions, but I'm just saying the diagonal line, essentially, versus what you see in the colors are not easily visible on Zoom, but the top two colored in the legend, SSMVR, which is actually it's top three. SSMVR is your sliced score matching. Variance reduced, I don't know VR what that is, but and DSM is the denoising score matching. So time wise, as you increase the dimensions, after like 300 or 400 dimensions, it's not possible to do the vanilla score matching approach, but the sliced score matching or DSM continue to scale pretty well. And then if you go 10 seconds forward, just with the mouse keyboard, the mouse thing, oh, sorry, the keyboard thing, yeah. And these are the scores which he'll talk about. So essentially, the left two are the SSM scores for the slice. So the leftmost is the slice score matching, and the orange one is the SSM only, and then I think SSM VR is the leftmost, which is almost same as the rightmost, which is the vanilla score match. You know, when I say vanilla, you know, the what's the right word to say that? Non-optimized or I'm you know
the full score matching.
The full score matching, not yeah. So the performance, this is the actual score measurement, you know, the loss, if you may, and not loss. I mean, when it says minus 30, it's not that. It's like how close it is to the actual score, and also you look at the confidence interval there. So essentially, the slice score matching is pretty close, but then as you mentioned, that still is a lot of I mean, that can be optimized performance-wise with the green one, which is the denoise score matching. Even though the denoise score matching performance is on the density estimation is slightly less, but in terms of the time performance, it scales pretty well. I think that was your question earlier, Ted.
Yep. Nope, that's good. Just to see that it actually works.
Yes. And so far, I did mention that in the chat, but so far he's only talking about how instead of trying, why this method to estimate the probability density is a better approach overall. And now he will use this score-based matching to start sampling, because so far there's been no generation of image or anything. It's just training the score function, neural network. But now he'll use that to start apply that to generate the images. And there will be some challenges, and then how they'll come up with a noise schedule and then correlation with diffusion over time. So that's the background setup for this.
All right, thanks, Dave. I'm gonna keep playing then.
Thanks.
And in terms of the actual performance of a score estimation, we report the results on the left figure. So the performance is better when the number is lower. So comparing sliced score matching and score matching, you can see that even though sliced score matching takes much less time to compute, they can still obtain more or less comparable performance as score matching in terms of a score estimation. So really, we gain a lot of computational boost at a small cost of the accuracy in score estimation. For denoising score matching DSM, because you have to inject noise to the data point, so the performance in score estimation is not as good as sliced score matching. We want to estimate the score function of a clean data point. So everything is well expected. So now I have discussed how working with score functions allow very flexible models, because score functions bypass the challenge of normalizing constant. And we can use principled statistical methods like score matching, sliced score matching, or denoising score matching to train those score models from data. For the next part, I will show you how can we generate samples from these models of score functions, and how can we control the sample generation process in a principled way. So as a quick recap, we know that given a large training data set, we can use principled statistical methods like score matching to train a score model to estimate the underlying score function. In order to build a generative model, we have to find a certain approach to create new data points from the given vector field of score functions. So how can we do this? Well, suppose we are already given the score function, and imagine there are many random points scattered across the space. Can we move those random points to form samples from the score function? Well, one idea is we can potentially move those points by following the directions predicted by the score function. However, this will not give us valid samples because all those points will eventually collapse into each other. But this problem can be addressed if we follow a noisy version of the score function. So equivalently, we want to inject Gaussian noise to our score function and follow those noise-perturbed score functions. So this method is the well-known approach of Langevin Dynamics. And it is also well known that if we keep this sampling procedure long enough to reach convergence, and if we set the step size to be very, very small, then Langevin Dynamics are guaranteed to give you the correct samples from the score function. So this is details of Langevin Dynamics sampling. The goal is to sample from some density px using only the score function, the gradient of px. And the procedure of Langevin Dynamics is as follows. First, we initialize our sample from some prior distribution. So this prior distribution can be very simple. It can be a Gaussian distribution, it can be a uniform distribution. And we repeat the following procedure multiple times. So in each of the sampling step, we first generate a random Gaussian vector from the standard Gaussian distribution. And then we modify X according to the following recurrence equation. So we basically update the previous sample using our score function plus a scaled version of the Gaussian noise factor. And if you set epsilon to something very close to 0, and if you set the total number of iterations, the capital T, to be large enough, then we are guaranteed to obtain a valid sample from the underlying density of the score function. So now we know score matching can estimate the score function of data, and the Langevin dynamics can generate samples from the score function. So it becomes very, very natural to just replace the score function in Langevin dynamics with our score model, and then we can generate new data samples. We define a new generative model. So this approach sounds very nice from the theoretical perspective, but it does not work well in practice. So here are the results of combining score matching and Langevin dynamics naively. The left figure shows some images from the CIFAR-10 dataset. So CIFAR-10 is a dataset that contains many images of size 32 by 32. And the right figure shows you newly generated samples by combining score matching and Langevin dynamics naively. So clearly you can see that the newly generated samples do not look realistic at all. So there has to be something very wrong with this simple naive approach. And in our research, we have identified several challenges. One interesting challenge is it is hard to estimate score functions accurately in low data density regions. So to illustrate this challenge, let's consider the toy example of a mixture of Gaussian distribution again. So the left figure shows you the ground truth density function. The middle figure shows you the ground truth score function. The rightmost figure gives you the estimated score function from score matching. If you compare those two vector fields, it's clear that the estimated scores are accurate in high data density regions, which are given by those green boxes. But for low data density regions, the estimated scores are not accurate at all. So this is not totally unexpected because we use score matching to train our score model. And score matching compares the difference between the ground truth and the model only at samples from the data distribution. So in low data density regions, we don't have enough samples, and therefore we don't have enough information to infer the true score functions in those regions. And this is a huge obstacle for Langevin dynamics to provide high quality samples, because Langevin dynamics will have a lot of trouble exploring and navigating those low data density regions. So how can we address this challenge? One idea is to inject Gaussian noise to perturb our data points. So after adding enough Gaussian noise, we perturb the data points to everywhere in the space. This means the size of low data density regions becomes smaller. So in the context of image generation, adding additional Gaussian noise means we inject Gaussian noise to perturb each pixel of the image. So in this toy example, you can see that after injecting the right amount of Gaussian noise, the estimated scores now become accurate almost everywhere. And this phenomenon is very promising because it at least says that those score functions of noisy data densities are much easier to be estimated accurately. And those score functions of noisy densities could provide valuable directional information to guide Langevin dynamics to move from low data density regions to high data density regions. But simply injecting Gaussian noise will not solve all the problem, because after perturbation of data points, those noisy data densities are no longer good approximations to the original true data density. So to solve this problem, we propose to use a sequence of different noise levels. So as a toy example, we consider 3 noise levels from sigma 1 to sigma 3. We use Gaussian noise of mean 0 and standard deviation from sigma 1 to sigma 3 to perturb our training dataset. And this will give us 3 noisy training datasets. For each noisy dataset, there will be a corresponding noisy data density, which we denote as P sigma 1 to P sigma 3. So in the context of images, perturbation using multiple levels of noise will give you a sequence of images demonstrated here. So after obtaining those noisy datasets, we want to estimate the underlying density. We want to estimate the underlying score function of the corresponding noisy data densities. So how can we estimate 3 noisy score functions? Well, the most naive approach is we train 3 networks, and each network is responsible for estimating the score function of a single noise level. But this is not a scalable solution because in practice, we might require much more noise levels. For example, on image generation, we typically require hundreds to thousands of noise levels. A more scalable solution is to consider a conditional score model, which we call a noise conditional score model. A noise conditional score model is a simple modification to a score model. It takes the noise level sigma as one additional input dimension to the model. The output corresponds to the score function of the data density perturbed with noise level sigma. So how can we train this noise conditional score model? Well, again, we can leverage the idea of score matching. We have an important modification of score matching to jointly train the score model across all levels. So in this modification, we have a summation of score matching losses. We have one score matching loss for each noise level sigma I, and we have a positive weighting function, lambda sigma I. So the value of this weighting function is typically chosen using empirical heuristics. It can also be derived using principled analysis of the problem. We have this positive weighting function just want to balance the scales of score matching loss across all noise levels, and this is helpful for optimization. So by minimizing this modified score matching loss, if our optimizer is powerful enough, and if our model is expressive enough, then we will obtain accurate score estimation for all noise levels. So after training this noise conditional score model, how do we generate samples? One additional note is that this mixture of a score matching loss function is actually a generalization to the training objective of the first version of diffusion probabilistic models proposed in 2015, and this connects score-based genetic models to diffusion models. The connection between score-based models and diffusion models was first unveiled by the DDPM paper, which was in 2020. So now let's return to the question of how to sample from the noise conditional score model after training with the score matching loss. Well, we can still use Langevin Dynamics. We can first apply Langevin Dynamics to sample from the score model with the biggest perturbation noise. And the samples will be used as initialization to sample from the score model of the next noise level. And we continue in extension until finally we generate samples from the score function with the smallest noise level. We call this sampling procedure annealed Langevin dynamics because the rough intuition is we hope to gradually anneal down the temperature of our data density to gradually reduce the noise level. And this is what it looks like when we apply this approach to modeling real images. So it's quite remarkable that we can start from random noise, then modify those images according to the score model, and this can eventually give us nice looking samples. And this is the result of simple noise condition.
Yeah, so I mean, we didn't pause for a long time, and he went through a lot of details of how they went from sampling, Langevin Dynamics space sampling, which did not yield good results, and then they injected noise, but that also did not work well, and they had to come up with this multi-level, when I say multi-level, a schedule of noise, essentially injection and the score matching. And then when they started doing the noise conditioned score matching for each of those different noise levels at different phases, if you may, and then they got the good result, which sounds in principle just so similar to diffusion model, except that that correlation was established back in 2020, after he introduced this whole thing, the noise condition score modeling. The other thing that I wanted to mention, which I put in the chat as well, was that because this was not correlated with diffusion in the beginning, so the terminology was slightly opposite. It was opposite of how we see it in the diffusion papers. So in the diffusion papers, X0 is the data set image, if you may, and XT is the noisy image. But in this case, he samples noise from some distribution uniform or Gaussian, the pi x that he mentioned, and that is X0 and goes towards XT. So I don't know if you'll change the notation for the rest of the paper, but something that we should keep in mind in terms of diffusion versus his approaches. Ted or others or Sally, if you had any comments, just let us know. Otherwise, we can continue.
Yeah, no, I thought his explanation was very good. So when you're doing sort of this random walk in the very highly perturbed score function, hopefully that gets you away from the super lowest low probability density areas, right? And then as you lower sigma, then you say, okay, I don't have to worry about my score function being wrong in these ultra low density areas because I'm probably not there anymore. I just need to get it in the low, and then you do that, and then that hopefully you're no longer in any of the low probability regions. And so then you use slightly smaller, right, until eventually you're nearish to one of the high probability distribution areas. And then you can just use sort of vanilla with very little noise and get an accurate, I'm saying
sample, yes,
somewhat loosely, but a random walk to get a decent sample from the true probability distribution P of X.
Right, and there's no collapse. So because if we do not have that noise, then it will just collapse to the.
You'll find all the modes, but you won't sample from the distribution. Yeah. Dave, did you have a comment?
No, that's also. And I don't want to talk more about the loss that we had in diffusion versus here. But in some ways, the original paper diffusion loss was derived on variational inference of the estimation for not the score. Of course, they didn't use score in the 2015 paper, but for the probability density at each diffuse layer or each time step, if you may, and which in some ways, as the original author would also describe sometimes, was like a variational autoencoder for each layer. But this one is, score matching is different. So, even though there is that noise and, just like how we do reparameterization trick in VAE, so you can think of in some ways, there's some noise, and of course, in the diffusion model equations, there's the reparameterization trick, even in the actual diffusion model as we do today also. But there's no assumption about, like, VAs assume the Gaussian distribution for each of the latents, right? Here, there's no assumptions about the probability distribution model for the latents. So again, he'll, just restating what he has said or done work on in different ways and kind of re-emphasizing. He'll probably say that again, or has said that in the past, but just re-emphasizing those things, that how and why it is so powerful model.
Hey, Dave, quick question. I'm just going to go backwards a little bit. Let me do this.
And while we are doing that, I just want to let you know at around 7:40, I'll have to go for around 10 minutes.
Okay. Oh, this was farther than I realized. Sorry. But what I was going to say is I've looked at the Saul-Dickstein paper. That's like the first diffusion one that often you see referenced in new papers. And then DDPM is Ho. If I remember right, on Yang Song's blog page, he just said that the connection between diffusion and score matching was first unveiled in the 2020 paper. But he didn't actually say what that connection is. I think on his blog he does actually share the connection, how to see the two of them are equivalent, right?
That's correct. Yes.
Okay.
Yeah, he does say that on his blog, and I can quickly look at that
All right.
if you
You want
want.
to maybe
We
put
can.
something in the chat, or if you find something
Yeah.
more specific? Yeah. But my whole point was
I'll
just
do
that, like, he says it's equivalent, but then he just waved his hands. He didn't actually walk us through that equivalence.
Right.
But
I'll
so
put
I
in
would
the
say,
chat.
that if people are looking to read more, these two papers are both pretty good papers. They're pretty readable. I found both the Saul-Dickstein and the DDPM paper. And so then, and then you can also look at his blog. Sorry, going back forward. Okay. So he's talking about this thing works. His first neural network model that he built when he did this annealed score matching, he called it NCSN, the noise conditional score network, I think. So then he's going to show empirical numbers. Hey, I did this, and here's my rockin' awesome state of the art at the time image quality scores.
So, Ted, if I may, before you start, so I will just read what it says on the blog, and of course, I saw Shulin put the link to the blog on chat as well. So, in 2020, Jonathan Ho and colleagues significantly improved the empirical performance of diffusion probabilistic models, and first unveiled a deeper connection to score-based generative modeling. They showed that the elbow, which was used for training diffusion probabilistic models, which is also the same criteria that we have for VAE, is essentially equivalent to the weighted combination of score matching. We saw some weighted combination of variance there for different noises. So what they established was that the elbow used for training diffusion probabilistic models is essentially equivalent to the weighted combination of score matching objectives used in score-based generative modeling. Moreover, by parameterizing the decoder as a sequence of score-based models with a unit architecture, they demonstrated for the first time that diffusion probabilistic models can also generate high-quality image samples comparable or superior to GANs. So I think that was a big difference, or how when they brought in score-based modeling and used elbow for training diffusion probabilistic models.
Okay, so Dave, there's a question in the chat. So the score function is just the gradient if you take the log of the probability density function. Can you answer like score matching, what that process is? There's a score function, but then there's score matching.
So so score matching is, so let's say you have so you have some score function that your network is predicting, and based on your data points, you have the estimate of your score just on your data points. And what you want to do is that you want to build a function, a network that is going to give you as close a score as what your data point score is, right? So you're building or training this network so that the score predicted, that score that you see based on your data points is the score predicted by your network is getting as close as possible to the score that you see or can get from the data points. I don't know if that answers the question, but essentially that's what you're trying to do with that. I don't know who was asking that question.
I'm going to try and prove Selly's point, because I think this is a great question. and I'm not sure if I understand this topic well enough to understand to answer it. But like, if you look at this upper left image, okay, he's using this to demonstrate something else. But just look at this. Imagine you have only a two-dimensional problem, and the blue dots are your actual data points from whatever. So right, these are our dog pictures or something like that, right? So if you have these, you will have an empirical probability distribution. And I'm not sure exactly how you do it, Dave, because you don't want to treat each of these points as a single point density. But if you like, I don't know, put like a little Gaussian centered at each of these points and you sum them all up, you would get some probability distribution. And you could take the log of that, you could take the gradient of that, and essentially that's your empirical score function. And what you're doing is you're trying to build a neural network to match that, to predict it. Is that what we're doing? Did I get that right?
That at least is my interpretation. I mean, you
Yes.
captured exactly my interpretation. Because to kind of grab your sentences halfway through, right, to attempt to not only empirically but declaratively describe such a distribution. I mean, I don't know that I would say it's impossible, but like for those of us that are religious, like that would be like the equation, right? Like in kind of a sense, right? Like you've written an equation for dog, right? I mean and instead what we've done is we've kind of made the observation that the dog images exist kind of proximal to one another in some massively multidimensional space, but that the only way to approximate that is via a neural network and not declaratively empirically.
Right. And I think last week somebody else asked about like Markov chain Monte Carlo, and like, yes, that is another technique for estimating the density, the probability density of a certain distribution. And I can't, again, I don't even want to try to speak to like why this, why that, but you can see in this case, he has developed these performance optimization, the sliced thing, where you integrate, you know.
I can answer that right off the bat, right? Like if you look at annealing, why do they only use annealing Monte Carlo infrequently? Is just the cost of computation, right? On a 10-dimensional problem. So now let's do that on a million-dimensional problem. And I mean, Monte Carlo, as much as I love it, just by the nature of a single iteration, I think would become intractable.
Yeah. So I think that's sort of the answer, is just you got to find a problem for which you have a reasonable computational ability to do it. And I don't know, like, I don't know what Yang Song was thinking when he's in graduate school and just sitting at his desk, staring at the wall thinking, but like, clearly, fast forward a few years, we can say, yeah, this technique clearly works, because we would not have MidJourney if this technique didn't work.
Well, I think the other thing, if you tie that back to Roger's presentation like 2 weeks ago, performance is fundamentally tied with quality of outcome. When we're kind of at this event horizon, where like to run a simulated annealing using Monte Carlo would probably take, you know, to the cold death state of the universe in a problem like this, right? Which is a long time to wait for those of you that aren't familiar with that.
So for the question in the chat, did that answer your question? Okay, awesome. All right, so I think he was starting to talk about his numbers, and let's see here. Yeah, so Dave, I don't know if you're going to be back before we end at 8, but so I'm planning to just play through a little bit and pause when we get close to the top of the hour.
Okay, sounds good. Thanks.
Additional score model approach in 2019. So we provide inception scores and FRD scores on CPA10 dataset. Those inception scores and FRDs are important quantities for comparing the performance of different generative models in terms of sample quality. So this was the first time that a different method can outperform GANs in terms of achieving higher inception score. So of course, FID score is still lagging behind GANs, but at that time, it was quite surprising that a simple approach can already outperform GANs in one important metric, which is the inception score. So why it is important to outperform GANs? Because GANs were the best genetic model for sample generation, especially for images, for quite a while. And as the Turing Award winner, Yan Kun has said that GANs are the most interesting idea in the last 10 years in machine learning. And indeed, GANs have attracted a lot of research efforts from big corporations and universities, and people have improved GANs so much, spent so much engineering effort on it. It is amazing to see that GANs can generate very nice looking images. But it is quite amazing that we can actually outperform GANs with score-based genetic models. And with the resource available in academia, we actually do not have much capability to tune those kind of score models well enough. So especially considering the imbalance between computer resources and engineering efforts spent on GANs and score-based models, I consider this as a very surprising achievement. So of course, noise conditional score models can be applied to other type of image generation tasks, including images of different objects and of different resolution. So with some later development on score matching techniques and the neural network model architectures, we can further improve the sample quality on CFI10. And of course, nowadays diffusion models have captured so much attention, and people are now working on diffusion, trying to improve their various perspectives. So it's not unexpected that people are achieving better and better quality using diffusion models or score-based models. So in this work, we again tackle the dataset of CFI10. The left figure shows some existing training images from the CFI10 dataset. The right figure shows the newly generated samples from this improved approach. So now you can see the newly generated samples look very realistic and very diverse. They're also different from existing training images. You cannot generate such images by simply memorizing the training dataset. And again, we compare with the best GAN approach in terms of FID scores and inception scores. So now we are able to outperform the best GAN approach in terms of both FID scores and inception scores. And this means score-based models can challenge the long-time dominance of GANs in image generation. The same approach can be extended to generate images of.
Sorry, just two really quick comments I wanted to make, just editorial comments. So one is, it's very cool that that these models are able to generate, realistic images, but also that he mentioned the diversity. So this is not some distribution that's sort of like close to a unimodal distribution. This is a distribution that has like many small modes all over the place, and it's actually doing really great for that. And so it's not like if you train this on dogs, you'll only get dogs in one pose or only get one breed of dog. You'll still get like tremendous variety. So I think that speaks to the strength of the true coverage of the whole probability distribution, not just capturing a few modes. The other thing I thought was kind of funny is he just said, and if I
could interrupt just for 1 second, not only the the distribution, but the discovered dimensionality, right? So underpinning that distribution, one of the interesting things about a neural network is that it doesn't enter predefined space, right? It's also discovering the dimensionality against which it's describing these PDFs. Yep. And that's one of them. Again, you throw in the word semantic, right? Like that the thing that we call a dog does have this kind of semantic space that can somehow be described in pixels, right? Which is obviously how we recognize them as dogs. And if you're watching Ashoka, you recognize the thing as a rat dog, for example. If you haven't watched Ashoka, you should watch it.
No spoilers. No spoilers.
Oh, sorry.
Yeah, no, that's cool. The other thing I just personally thought was kind of humorous is he said something like the long time dominance of GANs, meaning 5 years.
Yeah, 4 years, 3 years.
Because that's like now like 2 generations in the world of, right? It's like my grandfather used GANs, you know, like 5 years. That's like, yeah. So
It is pretty rad how fast we're moving right now.
Yeah. But he is right. Like, it wasn't a flash in the pan. It really was, quote unquote, long time in the world of today's world of ML. So, all right, I'm going to keep going.
A very large resolution. So here are 2 samples generated from a score-based model. Each one has the resolution 1024 by 1024. And here are more such samples from the same model with the same resolution. So you can see the samples are very high quality, quite comparable to the best GAN approaches and then time. So one remarkable property of a score-based generative modeling is the capability to control the generation process in a principled way. So suppose we are given an unconditional score-based generative model that generates images of dogs, but we want to that generates images of both dogs and cats, but we want to only generate images of dogs. So how can we do that? Let's suppose we're given a forward model. So this forward model is basically an image classifier that gives us the label of an image Y from any image X. We want to specify a control signal, which is a target label Y. We want to specify the target label to be dog. And then we hope to sample from the conditional distribution of X given Y. This conditional distribution will provide images of dogs only. It is called the inverse distribution because you can view it as a probabilistic inversion of the forward model. So how can we obtain this inverse distribution? The standard approach is to leverage the Bayes rule. So in Bayes rule, we have access to the unconditional distribution Px. We are given the forward model, but we don't know the denominator. So this denominator is exactly the normalizing constant of the inverse distribution. This means we can use score functions to again bypass this challenge in Bayes rule. And we can derive the Bayes rule for score functions very easily. So the derivation is very simple. We just take the logarithm on both sides of Bayes rule and then take the gradient. Again, we can find that the only term that depends on the denominator goes away. The score function of the inverse distribution now becomes a simple summation with 2 terms. Well, the first term is the unconditional score function that can be estimated by training an unconditional score model. The second term is the gradient of the log forward model. In this particular application of conditional image generation, the forward model is a classifier, and the gradient can be very easily computed using bank propagation. In some other applications, this forward model might be manually specified, and the gradient is actually analytically tractable in most cases. So the nice thing of this decomposition is now we can plug in different forward models for exactly the same score model, which means we only need to train our unconditional score model once. Then we can repurpose this unconditional score model for various conditional generation applications just by switching the forward model. This is one example. We can train one unconditional score model of CIFAR10 images, then couple it with a classifier to generate class conditional samples. Here, the forward model is a time-dependent classifier. It is time-dependent because we consider a sequence of score functions, and this means we need to have a sequence of classifiers. So the figures demonstrate the conditional generation results of CIFAR10. We have like birds, we have deers, all from an unconditional score-based model. And this approach has been further.
Hey, by the way, I don't know that Dave is back, but I think that this involves you actually put like a prediction head on top of your regular diffusion model that predicts which of the, like in this case, CIFAR10, CIFAR100, whatever, which of the 100 classes it is. And then once you have that predictor, again, you can just take the the gradient by back propagating through that. So if you set y to be bird, then you just get that signal back, and that's the value that you inject into this, the equation you showed on the previous slide. So I don't know if anybody knows off the top of my head. I believe that's what you do, is you do need to actually have this tiny model or tiny prediction head that you utilize at training time. All right, I'm gonna keep going.
Develop as classifier guidance or classifier-free guidance in subsequent works. And nowadays, it is the standard technique used in all the text-to-image generation approaches, like Dall-E 2 or Imagen. We can use an unconditional score-based model for image embedding. So here, the control signal is the masked image. We only know some partial regions of the image. And we want to sample from the inverse distribution, which gives us completed images from a partially observed image. In this case, the forward model can be directly specified using our domain expertise. So there is no need to train a separate model for this task. And similarly, we can apply unconditional score-based models for image colorization. And again, in this figure, you can see that our control signal is the gray image, and we can infer the colorized images from the gray images. The forward model can be specified manually. For this image embedding and the image colorization tasks, we will actually using the same unconditional score model. So this means that one score-based generative model can be used for both image embedding and colorization, demonstrating the flexibility of this decomposition of the inverse score function. And again, we can apply this approach to larger scale examples, such as colorization for images or resolution 1024 by 1024. So the same approach can be applied to convert stroke patterns to realistic images. And here is one example. Now the stroke patterns become the control signal, and we use an unconditional score-based model trained on realistic images only. They have no idea about what a stroke pattern looks like. We can develop the forward model by manual specification using our domain expertise. And this is another example, language-guided image generation. In this case, we are based on an unconditional score-based model. And the target, the control signal becomes a language description, treehouse in the Star Studio Ghibli animation. The forward model is given by an image conditioning neural network. So in this example, the score model has no knowledge of language at all, but it is capable of generating spatial images and conform with the language description. And this is another example. We can apply conditional score-based generation for medical image reconstruction. And we consider the special problem of computed tomography. So in this case, we use X-rays to shoot through human body. Those X-rays will hit the detector to form observations called sparse field sinogram. We can invert this physical procedure to obtain those cross-sectional medical image. So here, the control signal is a sinogram. The inverse distribution gives you the conditional medical images, conditional distribution of medical images given the sinogram. We want to consider the problem of sparse view computed tomography, meaning that we want to use as few X-rays as possible to reduce radiation. And this is a very suitable task for generative models because by training an unconditional generative model on large-scale medical images, our generative models can actually learn what a typical medical image looks like. It can learn very useful image prior, and this can be subsequently used to reduce the number of X-ray projections. In this case, the forward model is given by physical simulation, so there is no need to train any separate conditional model for capturing this forward model. And we can have some results on real-world CT datasets. We consider the task of using 23 projections while in contrast, typical traditional approaches require like hundreds to thousands of projections. So this is the result of a traditional approach based on compressed sensing. So using only 23 projections, you can see the medical image is quite blurry. Quantitatively, we compare the performance of different algorithms using PSNR and SSIN. Here are the results of two deep neural network-based approaches. So those methods are based on mapping projections directly to images. So they are kind of limited to a particular training setting. In this case, since they are trained on 23 projections, it is hard to adapt them to different number of projections later. And this is our fully unsupervised approach. So because we only train one unconditional score-based model, we do not train any particular model associated with this 23 projection. So that means we can adapt the same model to different settings, like changing the number of projections later after training. And this is the ground truth. So both qualitatively and quantitatively, you can see that this score-based medical image construction approach can actually outperform other deep learning methods, even though this generative approach is fully unsupervised, does not bind to a particular experimental setting, while in contrast, existing deep learning methods have to be limited to a specific experimental setting. So similar success has also been observed on accelerated magnetic resonance imaging as well. And there has been numerous developments of score-based generative models or diffusion models. They have obtained state-of-the-art performance on many other tasks. And this is already kind of outdated at this time, but I think it's worth mentioning anyways. So we can generate high-quality images for much more complicated dataset like ImageNet, and we can obtain outstanding performance on audio synthesis, text-to-speech generation, material design. This is actually a paper by MIT researchers, and also shape generation. We can also use score-based approaches for molecular conformation prediction and time series prediction. And there is a website called Score-Based Generative Modeling.github.io that includes a list of relevant works trying to build upon the technology of diffusion and trying to improve the methodology of score-based generative models.
Hi, Ted.
For now, I'm talking about how score-based generative modeling allows flexible model architectures, allows improved sample quality with a controllable generation procedure. The last part of it.
So now you'll start the probability evaluation, the infinite noise schedule, and noise levels, and then SDE and ODE optimizations for faster sampling. So I think
I'm interested in that, but yeah, with only a couple minutes left before we get to the top of the hour, I think this is probably a good place to pause.
Right. And sorry, yeah, I've looked at the video before, but I don't know if this presentation is so good that typically I didn't even have to stop once to go and look. Of course, the more you listen, the more you augment or solidify your knowledge about it. But this presenter Yang Song has done a great job of presenting this. But what was really amazing was this medical image reconstruction with that term that he uses, the forward network, right? So once they have established the generative model for the CT for whatever CT it was for, I don't know what section of the body it is, but nonetheless, so once they have established that, then when they go to different machines, all they need is a few samples of that machine to see, like a forward classifier, like this image. Yes, there was a, whatever diagnosis it is or classification it is. And then when they get the new sample with just 23 of those samples, they are able to apply that, what they call as the forward. I forget the term, sorry. But whatever they apply, using the Bayes equation there. So with a standalone score matching based generative model and a classifier trained separately, they are able to reconstruct the fine grain images with just very few images. This is just super amazing.
Yeah. No, I thought it was super impressive. But one thing I did wonder is if I go to the hospital and the doctor does a CT of me and I am just some complete weirdo, okay? And I have this like fibrous tissue in my, let's say this is a kidney, I have no idea what it is, right? And no training sample has ever looked like this, right? Then I don't know if this model would say that that's so out of distribution that it generates something that looks more normal instead of what actually my weirdo kidney looks like. Does that make sense?
It does. I don't know what the error rate they noticed. I mean, they have given the different metrics here, right? So PSNR and SSIM measures, but I mean, can there be samples that are so out of distribution, or a machine that is so out of, well, machine still, you have done some classifier, built some classifier on that, right? So based on some data on that, and you're just using that along with your base generative model. But yeah, I don't know how often that happens, and if that happens, that's a good question, Ted. I don't know the answer to that.
Yeah, because like I assume there's going to be normal things like ones with cysts, ones without, and older and younger. Oh yeah, that's fine. I'm not overly worried. But like, yeah, I'm talking about like way, 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 out of distribution. So be kind of curious to see what happens there.
Yeah, I don't know. That's a good question, Ted. Yeah. But again, I continue to be impressed with this whole technology or methodology, whatever you want to call it. Yeah.
All right. I think what I'm going to do is stop sharing my screen. And then I don't know if anybody else had any questions or comments. I hope you guys found today's content interesting, approachable. Jerry, you can stop the recording anytime.